Hey everyone, this is the final episode about PBR texture maps in Blender. This video is about the emission map. I'll go through the main ways to set up emission maps, what they're most commonly used for, and some other settings that might be useful for you to know about. So let's get started. An emission map allows specific areas of a material to emit light, simulating a light source directly from the material itself. An emission map typically comes in two formats, color or black and white. A color emission map contains both brightness and color information, meaning it controls not only how strongly each part of the surface glows, but also what color the light is. A black and white emission map, on the other hand, only controls the strength of the glow using shades of gray, and is typically used as a mask. In both cases, the brightness of the map controls how much light the material emits. White or bright colors produce the strongest glow, while darker values result in weaker or no emission. The colored emission map is typically plugged directly into the emission color input of the Principled BSDF. The black and white emission map is typically used in a mixed shader setup with a separate emission shader, where the map acts as a mask to control where the glow shows up. The colored emission map is set to sRGB because it contains actual color information. Most color textures, like base color maps or colored emission maps, are created to look correct with the brightness adjustment that sRGB applies. The black and white map is set to non-color because it's most often used as a mask, not a color texture. This tells Blender to read it as raw data, so the values remain accurate and unaffected by any color processing. I'll go over why the setups are a bit different for the color and black and white maps in just a moment. But first, let's cover a few things you need to actually see emission. The first is ambient light. Here I've set the world lighting to 0 so the emission is easier to notice. If the overall ambient lighting in your scene is too bright, the emission may be hard to notice because it will be drowned out by the surrounding light. Next, while the bright parts of the material stand out, they don't yet look like they're emitting light. That's because for emission to feel believable, the scene needs something for the light to hit or reflect on. When I turn on these walls, with a reflective material at the back and a rougher surface on the sides, the emitted light starts to bounce and reflect, making the glow effect much more convincing. Now it becomes much clearer that the brighter areas emit more light, while the darker ones produce only a faint glow. However, there is another way to make a material look emissive even if there is no geometry around to reflect or receive the light, and that is by using the compositor. This is especially worth mentioning because as of Blender 4.2, the bloom effect has been removed from Eevee, so now you need the compositor to achieve it. After pressing F12 to render, go into the compositor, enable Use Nodes, add a glare node, and set it to bloom. You need to connect the output to a viewer node to see the composited result. Then enable Backdrop if you want to see the result in the background behind the nodes. But I prefer to open a separate window, set it to Image Editor, and find the Viewer node in the drop-down menu. At first, nothing seems to have happened. That's because the emission strength is too low. But if you increase the strength and render again, the glow will appear. You can also experiment with the other glare types for different results. Now let me explain the difference between the two emission setups. I'll use the same black and white emission map set to non-color data on both sides for a clearer comparison. On the left, the map is plugged directly into the emission input of the Principled BSDF shader. On the right, the map is used as the factor in a mixed shader setup that blends between a Principled BSDF and a separate emission shader. Both use the same emission strength of 1, ensuring that the color in the emission is identical in both cases. Next, I've added a bump map, generated from a noise texture to the base material in both setups. Visually, they look similar at first. The base material is still visible in the darker areas of the emission map. However, the key difference appears in the areas where the emission map is fully white. When the emission is connected directly to the principled shader, it becomes a part of that surface, meaning all the material's properties, including bump and reflectivity, are still present. That's why you can still see surface details, like the bump showing through the emission, and the emitted light slightly reflects off even the glowing parts, making the surrounding area appear a bit brighter. In contrast, the mix shader setup on the right completely overrides the base material in fully white areas. There's no bump or surface interaction, just pure emission. So that area is no longer affected by any properties of the base shader. In short, plugging an emission map into the Principled BSDF keeps it part of the material, while using a separate emission shader with a mix setup isolates the glow entirely and replaces the material. This gives you more control, especially when you want the emission to behave independently of the base surface. Let me give you some clear examples. Here I have a PBR lava material. It includes all the PBR texture maps we've already covered in this tutorial series. It also has an emission texture map. The map is set to sRGB and is plugged directly into the Principled BSDF's emission color input. This is the most convenient way to set up an emission map. It also makes sense for this particular texture because the emission is designed to work alongside the normal bump, roughness, and metallic maps in a physically accurate way. So when downloading PBR textures, you're most likely going to set it up this way. You can adjust the intensity of the glow using the strength slider. You can also adjust the color using one of Blender's color nodes, such as the hue saturation value node to adjust the hue. But in most cases, this setup is meant to be simple and ready to use. Just plug it in and it works as intended without much extra setup. Next, I have a model of a Game Boy with a screen made using a basic Principled BSDF shader. I also have a black and white texture that I want to use as an emission map. I could simply plug the texture into the emission input and increase the strength. But what if I also want the screen's base material to emit light, not just the text? I could use a color ramp to remap the black and white values. That way I can change the white parts of the texture, which is the text, and also change the black parts, which make up the background. However, this only works well if both are meant to stay static. If I try to change the emission strength, both the text and the background will brighten or dim together. So this is a good case for using the separate emission setup. I can add a mix shader with an emission node. I set the emission map to non-color so Blender uses the grayscale values as raw mask data and plug it into the mix shader's factor. Now I can control the screen's emission and the text emission independently. But there's a small issue. When I turn the text emission strength to 0, it shows up as black. That's because the white parts of the mask fully replace the base material with the emission shader, and if the emission is set to 0, that's just black. To fix this, I can add another mix shader. This way, I can toggle the text emission on and off without affecting the screen and still control each one separately. This setup also makes sense in this case, since screens don't blend pixel colors. They replace them with entirely new pixel values to display different content. This setup is also commonly combined with a transparent BSDF instead of the Principled BSDF to make the black areas fully transparent, which is useful for effects like glowing text or stickers. Other examples of where emission maps are used include neon signs, where they light up just the text and logos while the background stays dark. They're also common in car lights, making only the headlights and brake lights glow. A light bulb might use an emission map to make just the filament shine, leaving the rest of the model unaffected. In sci-fi assets like this portal, emission maps highlight the glowing or powered parts of the machinery. And on laptop screens and keyboards, they help illuminate the interface and keys selectively. Similar to my previous tutorials, let me also say a few words about emission in Eevee. In earlier versions of Eevee, although an object appeared emissive, it didn't actually cast light onto its surroundings by default. To achieve this effect, you had to bake the indirect lighting into something called an irradiance volume probe. Once baked, the probe only provides static lighting, which means it won't update if the objects or lights move. For dynamic and true light interaction, cycles was always the better choice. However, with the release of Blender 4.2, Eevee now supports ray tracing with global illumination. This means that emissive surfaces can now contribute light to your scene. The only limitation is that this effect is still based on screen space, meaning the light will only be calculated if the emitter object is visible on screen. If the object is obstructed or off-screen, it won't affect the scene. Additionally, the back faces of objects are ignored, and the lighting from emissive objects can vary depending on the camera's perspective. As a result, while emission in Eevee has significantly improved, traditional lights remain the most reliable option for illuminating your scene in most cases. As I mentioned in my tutorial about opacity, the older ambient occlusion option is still available under the Fast GI approximation panel and can be used if you want a more stylized look. However, beware that switching to ambient occlusion disables mesh lighting and bounce lighting from emissive objects. You can adjust the resolution of ray tracing and global illumination using the drop-down menus. To improve quality, you can also increase settings like rays, steps, and precision. But if you decide to increase resolution or improve quality, just make sure to raise the sample count for both the viewport and final render to maintain consistency. Additionally, with ray tracing disabled, emissive objects will also no longer contribute to the scene lighting. It's also worth noting that blended materials are incompatible with ray tracing. Finally, when using the dithered render method, enabling ray traced transmission prevents the surface from influencing the lighting of surfaces that do not use this setting. So if you're using emission as a light source in Eevee, it's best to make sure that all affected materials use the dithered render method and with either ray trace transmission enabled or disabled. And that's it for emission maps. I hope you found this video useful. If you haven't seen the other episodes in this series, be sure to check them out. It's been a lot of fun making these tutorials on PBR texture maps, and I really appreciate all the support you've given me through your likes and comments. I'm excited to move on to other topics and different parts of Blender, so make sure to subscribe so you don't miss those. Thanks for watching, and I'll see you in the next video.